Greetings, Earthlings, and welcome to another episode of Raw Space Presents, where we feature great videos from partner channels. In modern times, astronomy and scientific discovery can often seem beyond the reach of regular people. Nobody I know owns a super collider or a billion-dollar space telescope. And scientists, those white-coated specialists whom we tend to place upon a proverbial pedestal, have years of advanced education and a mental repository of arcane knowledge that make most of the rest of us seem like Neanderthals by comparison. However, discovering new things doesn't always require fancy facilities or chalkboards full of equations. Sometimes all it requires is that we observe and pay attention. Here, our friend the Exoplanets Channel explains how a regular person like you or I can detect, for ourselves, a planet orbiting another star, an exoplanet. If you need them, subtitles are available for the video. Just click the CC button.
Hi guys, today I'm going to start a series of videos about how you yourself can easily detect and, therefore, discover exoplanets with the cheapest possible equipment. What I'm going to use is a telephoto lens, a CMOS camera, and an equatorial mount. I would really appreciate if you could please subscribe and, most importantly, activate the notifications. The method to detect exoplanets that I'm going to show you is transit photometry. I will look for a drop in the brightness of a star produced by an exoplanet crossing it from my line of sight. The exoplanet I'm going to detect is called HD 189733b, which orbits the K-type star HD 189733. This star has an apparent magnitude of 7.7 and the exoplanet produces a drop of 2.4% during a total of almost 2 hours. HD 189733b is a gas giant, but in future videos I will try to show you how you can detect potentially habitable exoplanets. So, the telephoto lens I use is the Pentagon 135mm f2.8, which has an aperture of 48mm. As you can see, it has a hood built in. The CMOS camera is the monochrome ZWO-ASI 120mm, which has a bit rate of 12. And the equatorial mount is the Skywatcher EQ32, which has a polar scope built in. I also have a dual-axis motor drive, but a simple one that only controls the right extension would be enough. How much money did I spend? Well, I bought most of these items second-hand from eBay, so I spent around 300 euros, but it is also possible to, for example, buy the equipment with some friends. Now, to set up the telephoto lens and the camera, I have these guide rings. In order to focus the telephoto lens, I have to separate it 33mm from the camera by using, for example, two M42 extension rings, one of them 28mm long and the other one 5mm. If the lens still doesn't focus, just unscrew it a little bit from the camera. The focal I select is 2.8 and the distance chosen is the infinite. How do I know when is the exoplanet going to transit the star? Well, in this case I'm going to use the exoplanet transit database. I look for the exoplanet, click on it, and then click on Show Transit Predictions for the next 365 days. I scroll down, and here I enter the coordinates of my location, which are longitude -8.8 and latitude 42.2. I click on Submit, scroll down, and here I see that the next observable transit will start the 7th of October at 6:56 p.m. and finish the 7th of October at 8:45 p.m. UTC time. But my local time is UTC +2, so the transit will start and finish 2 hours later for me. Also, I will start gathering data, for example 30 minutes before the beginning of the transit and another 30 minutes after the end in order to show you the difference in brightness. Once I have everything set up, I open the program that came with the camera, which is called SharpCap. I click on Cameras and select ZWO ASI 120mm. Then I click on File, Shortcut Settings, Fits as the preferred distill format, Apply, and OK. In Capture Format and Area, I select Mono 16 as the color space and Fits as the output format. In Camera Controls, I set an exposure of, for example, 5 seconds and a gain of 1. I click on Start Capture, Single Frame, and perform a sequence of captures. I introduce, for example, 360 for the sequence length and 27 seconds for the interval between captures, so the camera will take 2 photographs every minute. Finally, I click on Start. Once the transit has finished, I open a program called AstroImageJ. I click on File, Import, Image Sequence, Shortcut Captures, click any of them, Open, Use Virtual Stack, and OK. Here I click on this icon that says Perform Multi-Aperture Photometry. I introduce, for example, 7 for the radius of the object, 15 for the inner radius of the background, and 25 for the outer radius of the background. I click on Place Apertures, zoom in, and firstly select the target star, which is this one. And secondly, select any reference star that is not variable, for example this one. I press enter and wait a little bit. Finally, I can see that the plot shows a clear light curve with the beginning and the end of the transit. Here there is a gap in the data because there was a cloud passing. You can find all the links for the equipment, database, and programs in the description below. Alright, and that's all for today. Thank you very much for watching. Feel free to leave any comment, suggestion, or question below. Please like, subscribe, activate the notifications, and share this video if you want. Bye bye.
Thanks for watching. Make sure to go subscribe to the Exoplanets channel. The link is in the description. And if you enjoy space content, make sure to like and subscribe to Raw Space as well. See you next time.